What's special about measurement? Measurement consists of 4 main steps, 2 of which we've already discussed as part of observations, in particular of indirect observation. So we define the concept to be measured, and then we specify an operation that is linked to a directly observable property, and we argue why this link is valid and sufficiently stable. But now, in measurement, we're doing 2 more things. In the first place, we are specifying a measure and defining a unit. And that's a very important step that so far hasn't played any role in observations. So measures are there in order to compare whatever is observed with sort of a standard. And ultimately, that comparison is necessary because that allows us to count. It allows us to assign numbers in some way. But we need to have these comparison units first. And this might be, in distance measurement, it's the meter, or in mass measurement, it is the kilogram, or in the temperature measurement, it is the distance on the glass vial in which we have different liquids expand or contract. Now, what's needed for a good measure? In the first place, I think what is important is that the measure must, of course, realize in the right way the relevant property that can be compared. So, I know for distance measurement, you better have a measure, an object that actually is extended. So that you can compare it, you can lay it next to each other, next to something that you want to compare it to. And that's not conventional. There's a deep necessity here that it must correspond to the relevant property. But it's important. It's the property of the directly observable property, right? So in distance measurement, we are basically performing a measurement on a direct observation. We're observing an object directly, and then we're observing how many times our measure unit fits next to it or besides it, right? But in temperature measurement, we are not actually requiring the measure unit to have mean kinetic energy. Of course, it will have that, but that's not what we're comparing. We're actually comparing the distance on the glass column that it has risen, right? So in that case, it's first the operationalization to an observable property, and then it's the comparison unit to that observable property that is of relevance. How big or small this unit is, however, that's entirely conventional, right? So there's nothing natural about the meter being the meter or the kilogram being the kilogram. It was just set by convention, and the most important thing was that everybody follows it. However, when we specify these measures, then what we want is that they're also very stable over time. And this has been a big problem for most of these prototype units of comparison. So when people, for a while, like the meter and the kilogram, they are prototypes. So there's an object that exists that exemplifies exactly that, or as precisely as possible, that measure. Now, if you use that kilogram regularly in comparing the mass of other objects, then it will lose some material. It will actually lose mass. So it has been a problem in practical applications that weights over time lost some of their mass, and therefore measurement changed. So what we need also is that the measure is sufficiently stable. And of course, due to it, the whole point, some of the point of the measure is its conventionality. So it should enable as many people as possible to apply this unit in the same way, because it is, after all, a standard of comparison. Nevertheless, or maybe because of these many requirements, what we see is that in the history of measurement, there is an enormous effort to try to find the right measure. So here it's the attempt seeking for the right kind of distance measure unit, has changed many times. It started out from defining a certain distance between 2 points on the Earth's surface. It then went on to the crafting of prototypes, and then it moved on finally to natural constants. So in natural constants, here we don't use prototypes anymore at all. Instead, we're using theory and identify with the help of theory certain underlying magnitudes that we find repeated in a large number of phenomena. Complicated, but what you see here on the right is that the uncertainty associated with these different measures decreased by orders of magnitude. And that's one of the most crucial goals, that we don't have instability, variation in the unit every time we use it. And decreasing that variation has been the purpose for which, in fact, an enormous amount of effort has been put into it, until very recently. It was just last November that the international system of units was changed, where the last prototype, namely the prototype for the kilogram, was replaced by a natural constant. Until then, the kilogram was still defined to that object, with reference to that object that sits somewhere in a vault in Paris. So much for defining or specifying measurement unit. When we have specified that unit, then we're able to count. Then we're able to say, well, how many of a particular unit did we just observe in this particular case? So we can assign numbers. But assigning numbers sounds so easy, but it's actually quite an interesting and complicated process. Here is Patrick Suppes, philosopher of science, who said, we cannot literally take a number into our hands and apply it to a physical object. Right? Instead, what we can do is to show that the structure of certain phenomena under certain empirical operations is the same as the structure of some set of numbers under arithmetic operations and relations. Now note this, some set of numbers. The important thing here is that there are many of these. There are different ones. We have different mathematical structures that we could use in order to compare it to the structures of these empirical or these phenomena under certain empirical conditions. And these are typically distinguished as different scales. A nominal scale is simply something that uses numbers to assign names to things. So you want to distinguish, let's say, a batch of experimental vials, and you give them different numbers. And also, all important is that you don't give two the same number, because then you might mix them up. In an ordinal scale, like in Mohs scale of hardness, all you do is you order objects according to the qualitative comparison in a particular, with regard to a particular property. In an interval scale, you are like in the Celsius scale, you are now allowing for a comparison of distances. In the ratio scale, you're now allowing not only for comparison of distances, but also for comparisons of ratios, which requires a 0 point, like the temperature in Kelvin is such an example. In the absolute scale, you would say you would compare the absolute number. So, for example, when we count students or people generally, then there's no variation. We just want to each individual is a natural unit. And we can't divide it or multiply it and say, well, you're 2 students or 0.5. And that holds, of course, only for discrete objects, but we can, in a continuum, we can also say that even there we have an absolute scale, for example, in probability, because there we have not just a lower bound, but we also have an upper bound. So these are examples of that. The question is, if these are different mathematical objects, how can we characterize them? What is the crucial difference here? So different scales of the same type are maybe mathematically distinct, but they represent identical empirical structures. So think of temperature measurement in Celsius and Fahrenheit. Now, we assign different numbers, but we have a structural identity of the underlying empirical phenomena to be represented. So Fahrenheit assigns 32 degrees to freezing point, while Celsius assigns 0, for example. And we have a transformation rule. This is called a transformation of a positive linear transformation. So what we're saying is that we can transform the Celsius to a Fahrenheit scale or to any other scale. Or we can multiply it with a positive scalar. We can add or subtract an absolute term as we want to, and yet that new mathematical structure will still represent the same empirical features of an object or a set of objects that we measure. So, but that also puts certain limitations on what we can infer from such mathematical structure. So, for example, if a room temperature has gone from 5 to 10 degrees Celsius, can we then say that the room has become twice as warm? Because mathematically, we can, right? I mean, clearly, 10 is 5 times 2. So it seems that if we just consider the mathematical property of these scales, of the Celsius scale or the Fahrenheit scale, then sure, we have such a relationship. But interestingly, that mathematical operation does not reflect anything in the empirical structure of the system. And one way to find out is to say that, well, in fact, the Fahrenheit and the Celsius scale, they represent the same empirical phenomenon, right? So there should be, and we should be able to transform the Celsius into the Fahrenheit and then perform that mathematical operation on both and get the same result if this was supposed to represent an empirical structure. But it doesn't. So if you multiply 5 degrees Celsius by 2, then you get 10 degrees Celsius. However, if you first transform 5 degrees Celsius into Fahrenheit, then multiply it by 2, and then transform it back, then transform it back, then you don't get the same result. So in the Fahrenheit scale, that same relationship does not hold. And as these two scales are supposed to represent the same empirical phenomena, you therefore can conclude that, no, this is not something that you can actually infer from such a scale. Even though it has that mathematical property, it being an interval scale prevents you from inferring information about ratios from that scale to the empirical system. That's not always the case. In the interval scales, we don't have a natural zero. Zero is set conventionally. We, however, have a ratio scale for temperature measurement, Kelvin, with a natural zero, where 0 is defined as the absence of where no mean kinetic energy is present. right? So there we have an interpretation of what that means, that 0. And in fact, a shift from 5 degrees Kelvin to 10 degrees Kelvin is actually a doubling of the temperature. It is double as 1. Yeah? So you can say this, you can make that inference from a ratio scale, but you cannot make that inference from an interval scale. So what matters here is the kind of transformations that are permitted. Which particular numerical scales are seen to be identical. And here we can distinguish the different types of scales according to the transformation rules that are allowed. And we go from the least constraint, the nominal scale, where you say any transformation is allowed, except for that we must retain, we must not violate non-identity. So you all got maybe a student some number in our registration system for this course. We could change this, right? We could give you a different number. It would work just as well, as long as we make sure that we don't suddenly give 2 of you the same number. Then havoc ensues. So that's the only transformation that is not allowed for a nominal scale. In an ordinal scale, you can perform any transformation that retains the order. So any positive monotone transformation will do. But the only information, therefore, that you can extract from the scale about the empirical system is the order, nothing else. You cannot compare differences, for example. In the interval scale, already discussed that, is a positive linear transformation. In the ratio scale, you can only do a positive scalar transformation, so you can only multiply it with a positive number. And in an absolute scale, it's unique. You can't change anything. I argued for the particular requirements on measures, gave you a number of scale types, and distinguished these scale types according to the admitted transformations.